Hello again, students. So here's where I leave you for today. This is where we're going to talk about Gibbs free energy. Last video we introduced the concept of spontaneity and entropy. Well, now we're going to introduce Gibbs free energy, which is a better way in some portions of quantifying spontaneity. It's a more convenient way than entropy of the universe. So let's go ahead and get started. So this was developed by the mathematician J. Willard Gibbs, producing a new state function, G, in order to quantify the spontaneity. So Gibbs and entropy are both state functions, much like delta H, much like enthalpy. Well, this agrees with the second law of thermodynamics that say delta G is equal to delta H minus temperature times delta S. So T delta S. That typically we use Gibbs in terms of kilojoules per mole, similar to what we use for enthalpy. Temperature must be in Kelvin, and entropy is usually presented in joules per mole Kelvin, which needs to be converted into kilojoules in order for this calculation to work. But it agrees with the other reaction, with the other equation, which would be entropy of the universe is equal to entropy of system minus delta H of system over T. That basically, whenever the entropy of the universe is increasing, we see a negative delta G. The Gibbs free energy in the system is decreasing. The Gibbs free energy in the system is decreasing. Well, you see a negative Gibbs free energy. That basically, it's like you're pulling the spring back and it's ready to launch forward. But so the delta G is negative for any spontaneous reaction. So when looking at spontaneity, delta G is always going to be less than 0 if it's spontaneous, and if this is true, then the forward reaction will proceed. The larger the delta G, the more spontaneous a reaction is considered. However, spontaneity does not relate directly to speed. So kinetics is different from thermodynamics. That just because a reaction is spontaneous doesn't mean it's going to occur quickly. It just says that it will occur. And delta G being greater than 0 does not mean something will not work. It just means it's non-spontaneous and it will not work without outside work being done. And if a reaction is non-spontaneous, then the reverse reaction is spontaneous. So you would consider the combustion of hydrogen gas and air to be spontaneous, and it produces water as a byproduct. You can split water into hydrogen gas again, but that process is not spontaneous. It's non-spontaneous. It needs energy to do that, but it is doable. But what is left out is what if a delta G of negative is spontaneous and a delta G of positive is non-spontaneous. What about that middle point where delta G is 0? Delta G is 0 suggests that neither product nor reactants are favored, and the system is set at equilibrium. So when a system is at equilibrium, the Gibbs free energy has essentially run out, and so it does not, the reaction essentially stops. The forward reaction is equally favored with the reverse reaction. And so the idea is that as a reaction proceeds, the Gibbs free energy should slowly increase until it gets to 0. That's how all Gibbs free energies should set up. So let's do a quick calculation of this. delta H at 25 degrees. So T is 25. We have BaO, CO2, and barium carbonate. This is definitely spontaneous. 121, 3, negative 548, 393.5, 12.1, 72.1, and so one thing you should note, these solids, they have a significant amount of enthalpy, but they have very low entropy. Very low entropy. Barium carbonate has a little bit more entropy than barium oxide because it's a little bit more complicated of a molecule, but compared to CO2, CO2 as a gas is a lot more random. So let's look at this now. So our reaction is just going to be delta G equals delta H minus T delta S. Well, we have to find what's delta H. Delta H is going to be negative 1213.0 minus negative 548 and negative 393.5. Going to make those all positive because of minusing a negative. So, is this going to be exothermic or is this going to be endothermic? We will see. 548.5. It is still wildly exothermic. So it's negative 271.5 kJ per mole. Now let's look at our delta S. So we have 112.1 minus 72.1 and 213.8. 112.1 minus 72.1 minus 213.8. So this is negative 173.8. But that's joules per mole Kelvin. And at 25 degrees, that is 298 Kelvin. So let's go back to our equation. Gibbs is so negative 271.5 minus 298 Kelvin times negative 173.8, but we have to divide by 1,000 to get this into kilojoules. Get this into kilojoules. So negative makes that a positive. So the 173.8 divided by 1,000, but times 298 makes this whole term 51.79. And if we add that to the negative 271.5, the delta G for this reaction is negative 219, we'll say 0.7 kilojoules. 219.7 kilojoules per mole. So is this spontaneous? Absolutely. But one of the next things we got to think about is this always going to be spontaneous? And the answer is no. This is spontaneous here when the temperature is 298, but if the temperature were to change, if the temperature were to increase, the spontaneity would decrease. And eventually there's a magical tipping point at which the temperature is too high and it would decompose back into barium oxide and carbon dioxide. That you can imagine that point, and that's what we'll next need to be talking about. Well, the one thing to note is the naught. The naught next to the delta G, delta H, or delta S has a special meaning in that this is the standard free energy or standard enthalpy or standard entropy. It refers to the calculation of the values from the pure elements using standard set of conditions. That we're using pure solids or liquids, all gases are used at 1 atmosphere, all solutions are 1 molar. And because of the reason in this definition, pure elements for entropy and Gibbs are 0. And when calculating Gibbs free energy, we're assuming 25 degrees, unless otherwise told. But it's possible to have a delta G of formation for individual compound, or use delta G of reaction using only tabulated delta G values if it's at 25 degrees. So it's possible to do this real quick. I'm not even going to really set this up. I'm not even going to go there. The idea here is diamond converting to graphite. Diamond has a Gibbs, graphite does not, because graphite's the pure elemental form. So if we calculate the difference, we get a Gibbs free energy of negative 2.84. It's spontaneous. A diamond is not forever. A diamond will decompose to graphite. It takes high pressures to push graphite into a diamond. So at lower pressures, it will slowly decompose. But once again, this is a very slow process. Gibbs free energy does not tell us about kinetics. So it takes thousands upon thousands of years for this decomposition to occur. So we will not see it in most of our lifetimes. So with that in mind, so we don't have to worry about it. Diamond is for essentially forever. But as I was talking about previously, since Gibbs equals enthalpy minus T times temperature times the entropy, spontaneity is a temperature-dependent system. That at a high temperature, entropy will have a greater influence on the spontaneity. So we can imagine 4 possible scenarios based on the signs of entropy and enthalpy. Remembering that Gibbs being negative is spontaneous, Gibbs being positive is non-spontaneous. So we can imagine that if the enthalpy is negative, so it produces heat, and the entropy is positive, it becomes more random as temperature proceeds, that it's spontaneous at all temperatures. It's that yellow line. It's that yellow line that as temperature goes up, it becomes more spontaneous. We can imagine a scenario where entropy is negative and enthalpy is positive. So it's that red line. So it's endothermic and entropy decreases where it's never spontaneous. It's non-spontaneous at all temperatures. It starts above 0 and it only gets more positive as temperature increases. But it's the two ones where they're both negative or both positive, which are the kind of tricky ones. When they're both negative, that means you have a positive effect from entropy, but a negative effect from enthalpy. So at low temperatures or moderate temperatures, it's spontaneous, but at very high temperatures, it becomes non-spontaneous. It's that blue line, the light blue line, the bluish green line. When they're both positive, it's non-spontaneous at low temperatures, and then at high enough temperatures, it becomes spontaneous. It's the dark blue line. And so you can imagine these 4 different scenarios. Now, you could easily check them by just plugging in a temperature and seeing what the value would be. But to determine the key temperature, where the spontaneity inversion occurs, you're essentially finding the point where Gibbs is 0. Gibbs is 0, and you're solving for your T. You get enthalpy over entropy, keeping in mind kilojoules and joules. You have to convert one, or you're going to get a T that is really, really small. Remember, when temperature is really, really small, you're saying it's almost absolute 0. So either the enthalpy needs to be multiplied by 1,000, or the entropy needs to be divided by 1,000 to make this work. But you can figure out at what point would that occur. Real quick, before we move on to the problem and the end of our slides, I want to look at our scenario we had here. We had 173.8 and negative 271. So what temperature would this cease to be spontaneous? So negative 271.5 kilojoules divided by negative 173.8 joules. So with that in mind, if one of these values is positive, your answer is always going to be negative. But they both have to have the same sign, because temperature in Kelvin can never be negative. But so 271.5, if I divided by 173.8 and I did not multiply by 1,000, I get a temperature of 1.56, which is essentially almost 0. And as a temperature, that will not work. That is not going to be good. So times it by 1,000. At what temperature would this cease to be spontaneous? It's pretty high. 1562 Kelvin. 1562 Kelvin. So with that in mind, it's like, we'll just say it's approximately 1300 degrees C. You put this in a blast furnace, it'll break apart, but most of the time it's going to be just fine and dandy. So the last scenario, let's run this guy real quick. Run this scenario of what's the Gibbs and what point where this might change. So 3H2 N plus N2 goes to 2NH3. I chose this one because, hey, this will make the Gibbs easier to find. Now, when you're trying to find this inversion, it is very important that you know your entropy and enthalpy. You cannot just jump straight and figure out the Gibbs. You'll notice that NH3 is very similar to NH2. So, NH3 is very similar to N2, at least in entropy. But okay, so delta H is just going to be negative 46.49 times 2. 49 times 2 is negative 92.98. Because minus 0 and minus 0 times 3 is going to be... The delta S is a little bit trickier, so we're going to have to say 192.5 times 2 minus 191.5 and 130.58 times 3. Entropically, not going to be favored. So 192 times 2 minus 191.5 minus 130.58 3. Delta S is going to be 198.24. So, delta G. So we have negative 92.98 times minus 298 times negative 198.24 divided by 1,000. Negative 92.98 minus 298 times negative 198.24 divided by 1,000. Entropically, this is favored. Not by much, but it's favored. That's kilojoules. At what temperature would this cease to be favored? So we're going to take negative 92.98 times 1,000, and we're going to divide it by the negative 198.24. 92.98 negative 198.24. At what temperature? 469. So basically 196, almost 200 degrees Celsius. It stops working. Now we see right here this is an exothermic process. What did we learn back in kinetics and equilibrium? Well, in equilibrium we learned that this exothermic process, because heat is a byproduct, Le Chatelier says when we heat this up, or when we cool this down, we get a shift towards more products. So, if we cool this down, what's going to be changing in the Gibbs free energy system? Well, we're going to have a weaker effect of the negative entropy. At a lower temperature, entropy is going to play a smaller part when it comes to calculating our Gibbs for that system. And so at a lower temperature, we have a more spontaneous system, and so we get more products. Well, for this last video, I'm going to stop it here, but for this last video, we're going to look and try to differentiate Gibbs standard from Gibbs non-standard conditions and relate this to our equilibrium constant K. Have a good day.